Live floating meeting controls.
Yes. Can you hear us online now? Yes, excellent. Okay, sorry. Now for the online people, so MNT, what do? We need two pieces of information to get individual magnetic moments out. First of all, we need a high resolution surface magnetic field of the sample. And that is what we do with the QDM, because it can attain a resolution of 1.2 by 1.2 micrometers, pretty small. And then the other thing we need is the location of the particle. Which you can obtain with CT, since the particles are mostly very high density. So with CT, we can get them. And then by combining these two pieces of information, we can actually infer what the magnetic, what the magnetic intensity and direction actually is. But how do we actually go from that to that? I mean, it looks very simple, just measure it, but what do we actually need to do? So I'll try to go with you through the workflow of actually getting these individual magnetic moments out with MMT. And the first step, of course, is sample preparation. And as I already said, we start with, if we start from the regular bulk sample, we first need to create a thin section, which we need to glue to glass, because for the next step, we have to drill a tiny core from that. And if you would just have a loose sliver of sample, it would just evaporate and it's gone. So we need to put this on glass very carefully. And then after we have had this tiny core, it is important to polish the surface as flatly as possible, because that influences how well your results will be with the QDM, which we'll go to now, because that's the next step, of course, measuring with the QDM. Let me first tell you a bit about what a QDM is, more or less. I won't go into the details, but it is a very high resolution magnetometer. It does work with a, let's say, special diamond chip on which you shoot green laser light, and then it becomes susceptible in some way to magnetic fields, actually. I'm not going to go into the details of quantum physics because I'm not too familiar with that. You maybe. But what is important is that this diamond chip is very essential for getting a good image of the magnetic field. So when we did this at first, we noticed that our diamond became a bit smudged over time. And you might think, oh, wait, just to remove the smudge. Well, if we break the diamond, it's quite expensive. So actually we want to evade of getting the smudge on. And actually we discovered that this smudge came from the sample itself, because we shoot a green laser light on it, it is heated a bit, and therefore it releases some stuff on the diamond. So what we do now, instead of just putting it directly into the QDM, we first heat it a bit to 60 degrees to get away with that smudge, and then put it in the QDM. Which brings us to the next step, bringing that sample as close as possible to this diamond chip, because the closer it is, the clearer your signal will be. And at first we did this manually. It's a bit of a hassle, because there's a lot of twisting and things can go wrong. But then we had our technician, Bertwin, and he invented James. And James functions a bit like a butler, hence the name James, but it has a backronym, so don't worry about it, it's fine. What it does is you put your sample in James in a certain sample holder, and it will move it up as close as possible to the diamond chip. And it will stop until it feels a touch. And then it will tilt in every direction to ensure a parallel as possible position to the diamond chip. And that is very good, because then in 15 to 45 minutes, James has positioned the sample in such a way that we go from non-parallel measurements, as you can see on the left side, where you only have some focus on the bottom side of the sample, to almost a complete sample that is good in the field of view, and therefore constraining the sample to its distance. So after you've done your measurements, you can choose to, for example, get it out of the QDM, demagnetize it to a certain degree, and then put it back. You can't really put it in an oven, because if you put this tiny sliver in an oven, it will just break. That's not really an option, but demagnetization is certainly possible. Well, after you're finished with it all, you can go to the next step, which is actually CT imaging this sample. And for this, we mostly relied on the NanoCT in Oslo from the Faculty of Dentistry. Rose has some good connections with them. And they, within the XI program actually, so they will go back, we get their data back, which we then process in Dragonfly software, this open and really, really handy. I will say a bit more about it in the next slide, but without this software, which is actually Richard Harrison told us, oh, you should use this, and we're like, oh, this is a handy piece of software. Yeah, and then the aim of the game is getting these iron oxides out of the CT image with an expected or a reported resolution of about 415 nanometers. You might think, oh, that is not that low, especially if you want to see the single domains, part of the pseudo single domains. But we're having here we want to see the complete sample as well. And if we go smaller, the total size is reduced. So with this CT image and the QDM image ready, it's time to map the data. They have to be put in the same coordinate system if you want to say anything about the individual magnetic moments. And at first, so 4 years ago, this was a manual procedure by Marta, and it took her 2 to 4 weeks to map these two data sets, and it was really horrible. She never wanted to do this again. Partially why this was so difficult is that the CT in white and the QDM scan didn't overlap. So she was really searching in the sample where these two pieces should be, which is why we now want to see the whole sample. But now with Dragonfly, life becomes so much easier because you can load the CT data and you can load the QDM data at the same time. You might think, is this QDM data? Well, actually, this is the LED image made by the QDM. And this LED image of the QDM helps us in mapping the data to the CT. So yeah, I try to have a little panel over here, and then you can see in a different colors we have the grains extracted from the CT data, and we can actually put them very precisely on the QDM data set. Actually, it could do it that precisely that we actually discovered that there was a discrepancy in the CT resolution because it was reported to be 450 nanometers, but after some cross-verification, it was even smaller, like 400 nanometers. That's a really good program. Okay. So after that, I have the QDM scan with the sources, so with the individual iron oxides. And then it is time to calculate the magnetic moments, for which we have developed a Python package, MMT multipole inversion, mainly written by David, our postdoc. I contributed a bit to that. And this allows us to calculate these magnetic moments in a matter of minutes, where at first this took weeks and it was written on Fortran and it was not very optimal, but now it's all streamlined, optimized for GPU, CPU, whatever, it all works. What does it need? Well, magnetic data, of course, precision of the grains, so where they are, the expansion limit, so do we want to solve for dipoles, quadrupoles, octupoles, so think a bit about this as in geomagnetism, but you also have those dipolar components, octupolar components, quadrupolar components. And then the third or fourth parameter we need is the sample to sensor distance. You might think, oh, but you just introduced a machine that brings this sample as close as possible to the diamond chip. So isn't this just zero? Well, not actually the case, because this machine is designed to stop if it feels contact. And this contact doesn't necessarily mean that the sample touched the diamond, but it can also mean that there was some dust or a little grain protruding. So we still need to cross-verify the sample to sensor distance a bit to know with what value we're actually dealing. And for that, we rely on the algorithm of Gelson, actually, the Euler deconvolution, because that gives us some estimate on how far away the nearest sources are. Well, if everything is arranged, you can calculate the individual magnetic moments, and then bam, there you have it. It's like a stereo plot full of magnetic moments. And what now? Yeah, it's quite a lot. Maybe even too much. And that makes sense because we forgot about, here we go, the intermezzo, numerical stability. Because we just assume that we can solve all grains we can see in the sample. But actually, this is not the case. Imagine if you have a grain which is very deep in your sample, the signal it produced, so the magnetic signal this grain produced at the bottom, will not be very well visible at the top. So when you try to assign a magnetic moment to this grain, it is more or less determined by the noise which we are actually measuring. So this magnetic moment of this grain would make no sense at all. At the same time, if you compare small and large grains, these larger grains will produce a stronger magnetic moment than these ones. So there's also some volume dependency over here. And then the last thing which you need to incorporate is that we have to deal with ghost grains. And what are ghost grains? Well, there are grains which are there, but also are not there. So they produce magnetic signals, as you can see, but we can't see them in the CT because the resolution doesn't allow us that. But we need to incorporate that as well if you want to rule out which grains are numerically stable and which grains are not. So we try to do that. We try to do in this next step to calculate which grains are stable and which are not with the help of a numerical model. Of course, you want your numerical model as realistic as possible. And one of the questions we had in the beginning is, how many grains are actually in a rock slice? And we had no clue because there was no grain size distribution at all to help us here. So instead, we decided to venture to this on our own and try to make our own grain size distribution for a Hawaiian volcanic sample. So with the help of the Excite network and University of Cambridge, we did some tips. Well, I don't have to explain it now because Richard already did. So thank you again. So we got our tiny grain fraction, and we got our large grain fraction, which you already have from microscopy. We combined them in a certain way, and this helped us to determine how many grains we can find in a certain thin section. And then we also have to give them a signal, because if there's no signal, nothing happens. And for that, we rely on the volume versus TRM trend of Dunlop and Özdemir, because this is one of the few things that actually gives us some idea of how big these magnetic moments should be. Again, if you have any better idea, tell me, I'm open for everything. But we are using this now. So by combining these two pieces of information, we can actually model a rock thick or a thin section. So using that as input to put grains with different volumes in this thin section and assigning them realistic magnetic moments, we can actually model a QDM surface scan, as you can see on the right side. And what we then do is we go back. So using this scan and using the position of the grains, which we could see with our CT, we can actually calculate how many grains and where they are, how many grains we can actually solve. And this is lower than expected at first. It depends a bit on the sample thickness, because the thicker the sample, the more variables you have. But it is somewhere ranging between 15 to 20% to 5% of all grains we can see with the CT. Although for 30, 40, 50, and 60 microns, this is more or less the same amount of grains, because in here we have more grains, so that averages out. But this is quite low, so that's to the question, can we increase this number? And actually we can, by doing something very simple, which is just scanning two sides of the same sample. So scanning the top and scanning the bottom gives us twice the amount of data. And therefore, when we run through the models, we can actually resolve double the amount of grains as well. Okay, enough about that. We go back to our resolving magnetic moments. So what we can do now with these numerical models is go from the left picture, which has all grains in there, to the right picture, which only has the numerically stable grains. So already we removed about 80% of the grains, and we remain with this. So now we go to our recent results, and I already indicated a bit at the top. La Palma. So to give a bit of a background of La Palma, it is a volcanic island. It's part of Spain, and it is in the front of the coast of Morocco. So that's quite an interesting place. And my colleagues have been to this island in 2025 to sample a recent lava flow of 2021, so like really recent. And therefore we know where it should point. So it has a declination of -4, inclination of 37 degrees. And what she did, what Rosa did, is she brought the sample back, made thin sections of it, and then measured it in a QDM, but also demagnetized it. So she measured it in a QDM, then demagnetized it in the Z direction, etc., etc., etc. And when you then look at what happens on the individual grain level, it's quite interesting. So I have this example. So on the left side, we see a QDM scan of this sample in the NRM state, where I selected a small window in order to look at one specific grain. And on the right side, we look at the demagnetization step of 100 millitesla in the Z direction. And what is really cool is in the bulk, you expect, if you're demagnetizing, that the magnetic moment is becoming smaller and smaller. But actually on the grain scale, you see that it is not becoming smaller because this grain is either swept in the positive or a negative Z direction. So in the environment is, well, we have a grain over here, and this is its accompanying signal. And over here, it still has quite a big signal with an opposite. How does it look if we calculate the magnetic moments? Well, that is even more interesting, because the higher we make our demagnetization, the more and more it creeps towards the middle of the stereo plot, which means a steeper and steeper inclination, which makes sense if you demagnetize it in the Z direction. The intensity is also quite funny because it is very constant the whole time, except for that second experiment, but we have reasons to believe that it is due to some incorrect sample to sensor distance. So actually it is all quite the same. So maybe probably it is just fully saturated. This grain, by the way, is about 3 to 4 micrometers in diameter. Then what about bulk? Not really bulk, I should say. What happens if we would sum all these grains together? So not only this grain, but also the results of these other grains together. And then we actually see that the demagnetization does its job and the inclination is rather shallow, which is something we expect. At the same time, the intensity, we're not so sure about that, what's happening there. You expect it to go lower, but it fluctuates a bit. So if anybody has any idea why this is happening, please let me know and we can discuss this a bit further. Then the final step is actually rotating this back to the coordinate system we find in the field. So this is our QDM coordinates, the X and the Y. It's of course very interesting to see how this actually fits back into the field. So how we go from that thin section in the QDM back to the core drilled in the field. And then this is what we end up with. And interestingly enough, the declination seems to correspond, but the inclination is completely off. So we're still struggling here to find the best way to select these grains which are supposed to store the signal best and extract the relevant paleomagnetic info. I already got a small hint from Wellison on what we might need to do, but if anybody has good ideas, please let me know. But in the end, in these 4 years of MMT development, we came up with a streamlined workflow. We can now actually very easily process the results we get, and also we ensure reproducibility of the results. However, one important thing I forgot to mention is that regular bulk and QDM or MMT results cannot be directly compared, since the sensitivity of the two machines, so a machine for which you measure bulk and the QDM, are not the same. So they won't be directly comparable. Thanks.